Good morning, everyone. It's good to see you all here at the Canterbury House. I have the privilege and delight to introduce to you Dr. Tom Quinn, Professor Emeritus of Astronomy at the University of Washington. And the first thing I hope he describes for us is time travel, because I have to go preach right now. And it would be wonderful to preach and hear the lecture. I'm recording it, though, for posterity and for anyone who's not in our company. I'm going to open us up in a word of prayer. Heavenly Father, in your word it says, the heavens are declaring your glory and the skies proclaim the work of your hands. I thank you for Tom. I thank you for his life and his witness. And I thank you for the way in which this presentation can only draw us into a posture of humility, adoration, awe, as we contemplate the cosmos. So bless his words today. Bless our time together. In the name of Jesus. Amen. Amen. Let's welcome Tom.
Thanks very much. I think we ought to start by thinking about why would we be talking about astronomy in a church basement. But Jeremiah has started off that justification, and to continue the justification, I put up Psalm 19. And so we see, as in this example, many other places in the Bible, where God is calling us to look at the heavens and to think about what that says about his character and who he is. So it's appropriate for a church basement. On the other hand, if you're familiar with Psalm 19, you know that it goes on around the middle of the psalm. It switches and it says, what does it say? It says, the law of the Lord is perfect, refreshing the soul. And it goes on to describe the Word of God and its importance and meaning in our lives. So in that sense, we should be in the basement and not in the sanctuary. And that's going to be, I'll come back to that in a little bit. Okay, so that's a way of introduction. Let me also introduce myself a little bit more. Why would I talk about this stuff? So I am an astronomy professor at a research university. And what that means is I spend a little bit, well, I'm emeritus, so I still spend a little time teaching, and then a lot of my rest of my time doing research in particular cosmology, that is the structure of the universe as a whole. I think about how planets form, how planets and asteroids move through the solar system. And so that's the kind of work I do. And so I'm gonna, so let's give a quick outline of what I'm gonna do. So you're gonna get kind of a 30-minute astronomy 101. So I'll explain some of the things. If you look up in the heavens, right, perhaps you don't need me to instill awe, but I hope that giving a little explanation of what you're seeing will help you understand just a little bit more. So Jeremiah also prayed, but let's remember also at the end of Psalm 19, there is a little prayer. Let me repeat that. Lord, oh Lord, let these words of my mouth and this meditation of my heart be acceptable in your sight, O Lord, my rock and my redeemer. I should also say, I do have expertise in astronomy. The theology part, well, I'm an amateur there, and I look to others to get insight into explaining the Word of God, and including people in this room, which I'm indebted to for helping me to understand what the Scriptures say. So it says, this is Isaiah 40, look to the heavens. And to say again, you don't need an astronomer to say, look at this picture and get a sense of awe and wonder. But I will take a little time to explain some of the things you're seeing when you see these pictures of the sky. You know, you see them all over the web. And so I'll go through a few of them to give you a little explanation. So first of all, just a little tour through various objects in the universe. Then I'm going to back up and do a little explanation of how do we know what we know. And there's your Astro 101 lecture. And then at the end, I'm going to talk about how that relates to our understanding of God. So that's the outline of what I'm going to talk about. So let's start with this. So the quote you recognize is from Job 38. Very meaningful chapter of the Bible for me. And he says, "Can you bind the chains of the Pleiades?" And these are the Pleiades. So the Pleiades is a cluster of stars. There's hundreds of stars. People are usually familiar with like the 6 or 7 brightest stars in the cluster. These stars are quite bright. Each of these brightest stars are actually 100 or so times the brightness of our sun. And by the way, the star is another sun. Right? So each of these brighter than 100 of our own suns. They're in this picture, they're blue. In astronomy, blue colors tend to indicate very hot objects. Red colors tend to indicate very cool. And so these particular stars are about 10,000 degrees Kelvin, where our sun is only about 6,000 degrees Kelvin, and this room is about 300 degrees Kelvin, just to put it on a scale. That's an absolute temperature scale. So quite hot. The cluster has been around for about 100 million years. Probably some of the most brightest stars have disappeared by this time, which I'll explain in a little bit. And there's a myriad of not so bright stars in the background. The wispy stuff is interesting. This is what we call a reflection nebula. What we're seeing is the starlight being reflected off of interstellar material. We call the material dust. It's actually, physically, it's more like smoke from a forest fire. That's roughly the physical and chemical composition of this material. And so, can you bind the chains of the Pleiades? How well can you understand this? Is what God is asking Job. God also asked Job, can you loosen Orion's belt? So those of you who are familiar with the constellation Orion, you have the belt, and just hanging off the belt is Orion's sword, and this is an image from the Hubble Space Telescope of that nebula, just below Orion's belt. This is a very young cluster of stars. It's still halfway in the process of formation. There's a lot of gas and dust. There are very young, bright stars that are shining into this dust, and it's creating dust of all kinds of different temperatures, which is what the colors are representing. It is the nearest, I find this interesting, it is essentially the nearest stellar nursery to our sun. And I find it fascinating that this call to look at Orion's belt is juxtaposed next to God describing the births of the deer and the goats in the wild. And so here you're seeing the births of the stars. Absolutely fascinating. This is Hubble Space Telescope. It's kind of really zoomed in tight into one of these star-forming regions. Let's zoom out a little bit. Actually, zoom out quite a bit. Here's an image just taken this past summer at the Vera Rubin telescope down in Chile. It's just being commissioned. And this is quite a large patch sides of the sky. So the full moon, roughly that big on this image, so you're seeing quite a bit. There's lots of stars here, but there's even more galaxies, right? So as well as stars, actually, the objects that are obviously stars is actually this thing here. It looks kind of weird because it's actually too bright for the instrument, and it's actually saturated. You see some saturation effects there. Most of the rest of the objects you see are these things. These are galaxies. So that's a collection of stars, a large collection of stars, probably a few billion stars in that galaxy. And here's another one. Here's one that's a little farther away. We call this elliptical, just for the shape. I'll zoom into one of these spiral galaxies, which is more like our Milky Way. These kinds of galaxies, they're actually mostly flat. So that you're seeing face on. You'll see some, you look at this object here, that's a flat galaxy, which you're seeing edge on. So as you go, in fact, most of the faint fuzzy blobs you see in this picture are more galaxies. So each, again, with billions of stars. It's absolutely mind-blowing. Let me zoom in a little bit. Again, this is from the same, actually this is another part of the same image from the Vera Rubin Space Telescope. And you can see a little more detail on why we call these things spiral galaxies. They have this intricate spiral structure. The blue light is younger stars. The redder light is the older stars. Again, billions of stars, billions of stars. These two objects, they look right next to each other, but they're probably superimposed, right? One is a little more distant to the other, so they're not right on top of each other. These guys, on the other hand, it's clear that they're interacting with each other. So these galaxies can collide and make wonderful streams and intricate patterns that are absolutely fascinating. There's a lot in here. Let's look at this object here, right? So if we zoom in a little bit more, you see this is a cluster of galaxies. So here we have, again, each galaxy, a few billion stars. We have, these clusters tend to have 100 to 1,000 individual galaxies in them. They're all bound to each other. The galaxy in the center tends to be the largest, brightest galaxy in the cluster, and around it are a lot of smaller galaxies. Also in the image, you see a lot of faint fuzzy blobs. Those faint fuzzy blobs are also galaxies that are just so far away that you can't resolve them like you can these things that are closer by. Again, there's a few stars in this image. There's a star. There's a star. Those are stars in our own Milky Way, or the galaxy to which we belong. Again, they look kind of funny because they're so bright. They're saturating the instrument. Right, the instrument's sensitivity has been designed to look at these very faint things, and when bright objects get in the way, it causes these funny artifacts of diffraction spikes, we call them. So it's a cluster of galaxies. You see there's different shapes, different sizes. Absolutely fascinating. Let me tell you, so this isn't an image of the universe. This is an image of a calculation that I do. So what I do in my research is I build models of the universe. One of the things I'm really interested in is the nature of the dark matter for which we have it. And so I make calculations of what the dark matter distribution would look like because it attracts itself gravitationally. And one of the things it does is it creates this web, called cosmic web, throughout the universe. And if you look at this picture, again, computer simulation, calculation that I did, and you'll see that there's little knots. There's bigger knots at the intersection of filaments, and those are where the galaxies form. And so the thing is, right, I have a model of the dark matter, the universe. I run the computer calculation, crunch some numbers, make an image like this. I then make predictions of where galaxies ought to be, how they ought to be clusters, how many should be in each individual clusters, what are the shapes of the galaxies. And then we go out and look at what the universe actually does, and I make a decision, an evaluation of how good the model is. And it's not always right. It's not always right for a couple reasons. Usually the first reason is I made a mistake. Got to correct the sign in my calculation. But sometimes, right, we do not completely understand the universe. I haven't put in all the necessary ingredients, or some of the ingredients I have put in are wrong. And that's fine, right? That's the process of science, right? I have a model, I make predictions, hypotheses that model will predict, go through the calculation, makes the comparison. It's right, well that's nice, means I'm on the right track. If it's wrong, well that's more interesting. It means, okay, I don't quite understand what's going on, I need to think a little bit harder. And that's the process of what I do. So, just to be clear, a lot of what I might tell you this morning, it might be wrong. And that's okay. We're still trying to find things out, right? But then there's other things that I have to stand on for my daily life. And that's a little more important. Right, we want to be sure we get that right. Okay. Okay, that's the tour. I said we might be wrong. How do we know what we know? That's what I'd like to talk to you for a little bit right now. The basic principle that we go through is, we call it the cosmological principle. Some people call it the Copernican principle. The idea, for Copernicus, the idea is, well, the Earth is not a special place as far as its location. The cosmological principle is slightly different. It's, well, the physics on Earth is not special, right? It is completely applicable to other places in the universe. And so I have a list of physics that I'm interested in. And probably the primary example is gravity, right? So, we do the experiment, yep, it still works, okay? So we can get a stopwatch and measure the time it takes the keys to drop to the ground. I also measure the distance. Then you go back to your kindergarten physics class and remember that d equals 1/2 at squared, where a is the acceleration. You plug in the numbers and you get 9.8 meters per second squared. The insight that Newton had is you can do that same sort of calculation with the moon. And the same gravitational force that drew the keys to the ground is also drawing the moon to the Earth. Fortunately, so the moon is essentially falling towards the Earth. Fortunately, it always misses. And that's because it's actually moving sideways. It's falling as well as falling to the Earth. But again, the physics is the same. I can use the laws of gravity that I measure. Some of us down at the University of Washington, we're measuring how is the gravity between two bodies that are a centimeter apart. Is that any different than the Earth and the Moon? So far, it looks like it's still the same, which is absolutely amazing. So we use these kinds of calculations to understand body. So, and I'll go through another, we understand chemistry, more or less. We can look at gases in the lab, look at their properties, and apply those properties to the stars. For good or ill, we know how nuclear reactions work. We know how hydrogen turns into helium, how much energy that produces, quite a lot actually. And we can use that to calculate ages of stars, because the stars turn hydrogen into helium through nuclear reactions. Knowing the energy, knowing how bright stars are, we can calculate how long stars live. So to go into detail about the atomic physics, we can measure what we call spectra. We can take the light produced by an element and analyze it and work out what element is producing the light. And so these images are taken from laboratory experiments. You put, say, neon gas, you're probably familiar with. You put that in a little tube, you put electrodes on each side of the tube and excite the gas, it produces light. If you break that light up into its component colors, you will get this, we call spectra, individual colors. The neon is the color it is because of the concentration of emissions in this region. And I have, you probably can't read it in the back of the room, I have, along with neon, I have other elements, hydrogen, helium, sodium. You might be familiar with low pressure sodium street lamps emit in this yellow-orange, which you're probably familiar with. And here's mercury. Again, you can use these are essentially fingerprints that you can use to analyze starlight and understand what the composition of stars and the gas between stars is. The other thing you can do with these spectra is that if the object is moving with respect to you, if it's moving away from you, this pattern will shift actually towards the red end of the spectrum. Or if the star is approaching you, it'll shift to the blue. And it's called the Doppler effect. It's the same effect that's used in radar guns that the police use to get you for speeding. So we know quite well how it works. It's suitable for a court of law. We know how well that works. But we can use that to measure how fast things are moving away from us. And so when you're, again, looking at a picture like this, this is the Lagoon Nebula. Again, it's taken by the Very Rubin telescope down in Chile. You see all this pink light by bright stars. Well, that pink is the hydrogen being excited by the very intense starlight around a young star. All right, now I want to talk about how we measure distances to the stars. How do we know how far away things are? Well, in the solar system, it's kind of easy because we actually have been to objects in the solar system. So the Apollo astronauts have left retroreflectors on the surface of the moon. And this picture is taken from Apache Point Observatory down in New Mexico. This is the 3.5 meter, partly owned by the University of Washington. We're shooting a laser at the moon. Isn't that fun? And it's right, and the laser is bouncing off of one of these retroreflectors, and roughly 2 seconds later, the light comes back, and we can use that time delay of, again, around 2 seconds to measure the distance to the moon to the nearest millimeter or so. And you know, it's so accurate because we've actually sent a spacecraft there. Well, we sent people there. And other objects in the solar system we can measure with similar accuracy when we've sent, say, an interplanetary probe to them. So millimeter, centimeter accuracy in the solar system, because, and it's determined, right, another piece of physics, the speed of light, something we can measure very accurately in the lab, and we use that speed, and the moon, we measure it to be about 1 light second away. That's how long light takes to get there. We haven't been to the stars, so I have to come up with other techniques. One technique you probably know is triangulation. We call it parallax. And the point is, the Earth is not standing still over the course of the, year. There isn't a timer on that. Over the course of the year, the Earth moves around the sun, and half a year later, it's on the other side of the sun. If we look to a nearby star, it will be in a slightly different place. And so if you look at the image up here, right, this nearby star is over here in January. It's on the other side of the frame in July. And so we can use that motion to figure out the distance from the angle, just simple trigonometry. And that's how we get to the nearest stars. And we can do quite well with this. How far we go? So the nearest star, it's Proxima Centauri. I told you it took 1 second for the light to get from us to the moon. It takes, let's say, 4.2 years for light to get from us to Proxima Centauri. So that gives you the scale of the distance. Let's see, there are 30 million seconds in a year. So that's 3 years, so that's, how many seconds is that? That's roughly 100,000 seconds to get to the Proxima Centauri. So it's 100,000 times the distance from the Earth to the moon, which, by the way, the distance to the Earth to the moon is roughly 10 times the circumference of the Earth. Okay, so what does that come out to? Now we're 1 billion times the circumference of the Earth to get to Alpha Centauri. So these interstellar distances are absolutely enormous. And I give an example here. If the sun were about this big, to get the appropriate distance scale, we'd have to place the sun over in Spokane. Right? That's the relative distances we're talking about to get to this star. And we've measured quite a few distances. Actually, we've tried to measure the distances to billions of stars now. There's a European spacecraft called Gaia. It's measured many of the stars in the Milky Way. And so this is a picture of our galaxy of individual stars that were observed by the satellite, and a parallax measurement was attempted. And we can map out, all right, so this is, the size of our galaxy is about, turning it to light years, 30,000 light years across. We can reach out to about that distance and measure the parallax. So that's because the instruments is quite accurate. We measure it in arc seconds. So an arc second is 3,600th of a degree. And we can do tens of micro arc seconds. So 20 millionths of an arc second. But that gets us quite distant. You might recognize these objects if you've ever been in the south. Those are our nearest galactic neighbors, the large and small Magellanic Clouds. And we can, I mean, it's absolutely amazing. We can actually track how those galaxies are moving across the sky because we know the angles so accurately. So this gets us out sort of in our Milky Way neighborhood. If we want to go a little farther, we have to use another technique. We call it the standard candle. If we have an object which we know the brightness, we can use its apparent brightness to tell how far away it is. So if this is, wow, I'm not sure why my keyboard bouncing. So if I have a light bulb that I know is producing 100 watts, if it's closer, it's apparently brighter. If I move it, say twice the distance away, its brightness drops by a factor of 4. So I can get relative distances that way. If I have some calibration, it tells me what the number is, I can turn it into absolute distances. So do we have such light bulbs where we know have 100 watts stamped on them? Not quite, but we do have these objects. This is a supernova. This is one that went off about 1,000 years ago. And these things, A, are really bright, and they're roughly of constant brightness. The physics behind these things is we basically have a sun's mass worth of carbon and oxygen in an object that's about the size of the Earth. At some point, the gravitational force overcomes the atomic forces, and the thing deflagrates. All that carbon and oxygen burns into iron and cobalt, releasing an enormous amount of energy. The energy is so bright, it's basically 500 billion suns over the period of a week. And so we can see these things quite a distance away. If we look at one of these things, this is another galaxy. So this is an entire galaxy. This is one supernova, okay? And so when we see these things pop off, we can measure the brightness, and we can see them far away, and we can measure the distances. And that's how we map out distances on essentially a cosmological scale. And so we can make these maps of the universe. This is a map from the Sloan Digital Sky Survey, which I was involved with a few years ago. And so, each of these dots is an individual galaxy. It's a map, right? The Earth is at the center, and we know where every one of these galaxies is, how far away they are, where they are in the sky. And it goes out quite a ways. This is 100 million times the distance to the nearest star. And that's how far we're going out here. So things are really spread out in the universe. It's hard to comprehend how enormous this universe is. We can go look further out. Here's a cluster of galaxies observed by Hubble Space Telescope. So again, each of these blobs, like I was showing before, these are each billions of stars. The fascinating thing about this picture is that, if you can see in the back, right, there's these funny arc-like things, right? Those are individual galaxies that are behind the cluster. And the reason they have their funny shapes is because the mass in a cluster is lensing them, is bending the light and distorting it, so that we don't see the objects as they really are. We see distortions. And we measure the distortions, and we can turn that, right? We understand how gravity works, and we can calculate how much mass is in a cluster. And the interesting thing here is the amount of mass that you find in a cluster is several times more than the mass we can count up in the star. So there's mass out there we can't see. We label that dark matter, basically because, it doesn't emit, doesn't absorb, and we don't know what it is. But we can measure it due to its gravitational effects. As we look further out in the universe, you have to understand that time of flight for light now becomes important. It takes thousands of years to get to the nearest star. It's taking billions of years for the light from this object to reach us. So as we look further out in the universe, we're actually looking back in time. The other thing you might be aware of is that we see the universe is expanding. We use that Doppler shift to measure the recession of the galaxies. And we can, okay, the galaxies are moving away from us. At some point, they're a lot closer. And at some point, say 13 billion years ago, they were a lot closer. And so we can look, as we look further away, we can look back at the point where the universe was actually really dense. If it's dense, it's hot, another gas physics thing. And we can get a thermal image of the gas bucket at that time. And we can see this image in a microwave. So both with ground receivers, where it was first discovered. This is from a European satellite, measures the temperature of the universe way back when it was only 380,000 years old. And what you're seeing here is temperature fluctuation. So in this map, the red is slightly hotter, and the blue is slightly cooler over the mean temperature. And so we can study this gas. We know what this gas was, roughly 4,000 degrees Kelvin. We know how that gas behaves. We know how sound waves moves through it, and we can use that to make measurements of the distance scale. We can make measurements of how much the universe has expanded since this time to the present. And we get, another mystery. We find that in order to explain the expansion of the universe, we have to include a lot more stuff. So in this pie chart, this is the stuff we know about. Electrons, hydrogen atoms, all the other elements that we know about, all the subatomic particles that we know about fit in this wedge. This is stuff, I mentioned dark matter before. We see its gravitational effect, we don't know what it is. There's even more of something called dark energy, which we really don't know what it is. We just see its gravitational effect on the expansion of the universe. And so we put all that together and we can make a picture, all right? So, all right, this is a representation of the universe as a whole. And in the previous Canterbury house, Father Bruce has explained what a representation is. Right? We're not looking at the particular details, we're getting an overview of what's going on. And so the details are not what to focus on. What you're focusing on is the big picture. And so part of the big picture is that the universe has existed for a certain amount of time. We are here. The image was made by NASA, so that's why there's a satellite there. And then the vertical represents the relative size of the universe. And so what this is trying to represent is that the overall history of the universe, where there is an initial very rapid expansion, like in a few picoseconds, the universe expands by many orders of magnitude. We call that inflation. There's evidence for that to exist. We see this afterglow pattern, but the universe continues to expand, but not quite so rapidly. We have formation of galaxies and stars all the way up to the present. And the other mysterious thing is that this increase in the curvature here represents that the universe is actually accelerating in its expansion. So this is fascinating that we can do this. We're sort of stepping outside the universe and, shall I say, possibly looking at it as God would look at it. But hold on to that. Let's not quite go that there, because what I want to focus on is we don't know where. I think I made that clear. We don't know everything, right? And so we need to think about what we don't know. And in particular, contrast it to what God knows. So this is from Job 28. He, that is God, views the ends of the earth and sees everything under the heavens. So, do we see everything? Do we view? Right, so the ends of the earth, I should explain that, at least what comes into my mind. When you say the ends of the earth in, say, ancient Mideastern cosmology, right, you might remember the picture from the Egyptian mural, which shows the sky god in an ark and the earth god lying down underneath, right? So that picture is not just the earth, right? That is their entire cosmology, right? That's their picture of what the cosmos looks like. And so we have something similar here. We have a picture of what the cosmos looks like. But do we see the ends of the earth like God does? Do we see the future end? Right, yeah, let's go through the picture here once more. The future. Do we see the future? All right, so we're talking astronomy here. Will the sun rise tomorrow? Okay, you got that under control. It's kind of remarkable. Can we predict the time of the next lunar eclipse? Remarkably good at that. Can we predict the times of the lunar eclipses 10 million years from now? Not so much. I mean, the remarkable thing is that not only can't we predict it, there is no physical way we can predict it. That is, the uncertainty down to the quantum level of where we know the positions of the Earth and the planets are today does not give us enough information to predict what's going to happen to the solar system tens of millions of years from now. So we don't know the future end. Do we know these ends? Right, the spatial, what looks like edges in the universe. So as far as we can tell, actually, the universe goes on as far as we can see. And we're actually limited. Right? We can only see so far away because the universe is only so old. And so we can't see the end there. What about the beginning? Okay, so that might be a little more contentious. What do we know about the beginning? And, right? Lots of claims are made. Wow, perhaps it's evidence for God, right? That there is a beginning. But do we really understand it? Let me go to another expert here. Introduce you to this gentleman. Well, you know this guy. So this guy, his name is Georges Lemaitre. So this guy, discovered the equations for general relativity. Georges Lemaitre applied those equations and solved them for an expanding cosmos, as it appears we live in. So he's the first one actually to make that connection and actually infer that the expansion velocities that we observe the galaxies are related to this model of the universe, the Lemaitre model, we call it. And you see he has this collar here. So he's actually was a Catholic priest. And so he knows a little bit more, possibly I do, studying scriptures. And he had this, he knows a little bit more about general relativity than I do as well. So, I like this quote from him. As far as I can see, such a theory, he's referring to the Big Bang, remains entirely outside any metaphysical religious question. It leaves to the materialist to deny any transcendental being. Right? So you can't make a firm argument that, that's where God is working. Because as a physicist, you can continue to try to apply the methods of physics to try to understand that. And so he keeps for the bottom of space-time, the same methods that is used elsewhere, the non-singular places, as it calls it here. But let's pay attention to the last part of the quote here. For the believer, it removes any attempt to familiarity with God. So what's the point here? He's making the argument, okay, is God your buddy? Do you fully understand the ways of God? Clearly not. And in trying to attempt to understand the singularity, you're trying to make the claim, oh, this is God, how God created the universe. And what you fail to understand is that the creativity of God is so vastly greater than anything you can imagine. Right? And I think our tour of the universe, I hope, makes that clear. So, as we try to understand God's way, I think the temptation we might have is try fully to define God. You know, it'd be very nice if we put God in a box, right? We have a certain input, and a little while later, we get the same output. Right? I think it's pretty clear, that's not how God works. In fact, I find it interesting that, in the same passage where Isaiah calls, look to the heavens, right next to it, Isaiah 40:18 has this passage where he's actually ridiculing idolatry. I make the connection. Putting God in a box is the same as setting up an idol that you think you can control. And so, right, this works both ways. The temptation of the scientists, that's what we do. We put things in boxes, we test them. We expect reproducible results. And that's just not how it works. And I think I've already made this point, as a believer, we have certain expectations about how God works. And He surprises us, let's put it that way. And, going back to Job 28, right? The passage I referred to in Job 28 actually states where then can wisdom be found, and where does understanding dwell? No mortal comprehends its worth. It is hidden from the eyes of every living being. And so, we come through our life and we experience things. I can think of myriad things. Let's pick an example, say, estrangement from each other. Right? I've gone through that a little bit. Fortunately, we're on the other side of that. But I see it in other people's lives, a lot of pain there. And in the middle of it, you're asking, why, God? You don't see any particular reason for it. And even if you get a glimpse of a reason, you look back and say, is all that pain worth this? We don't understand how God works. Because we don't understand everything. Right? To keep quoting there, God alone knows where wisdom dwells. And so it's only in trusting Him who knows that we're going to be able to live in this world. And at the end of Job 28, we have, God, He examines wisdom, confirms it. And in the final statement, He says to the human race, the fear of the Lord, that is wisdom. And to shun evil, that is understanding. So what's He talking about here? The fear of the Lord is a little bit of a mysterious phrase. Father Bruce has helped me understand it a little bit. But one example is, let's go back to Psalm 19. Right? At the end of the psalm, it says, the Lord of the law is perfect, refreshing the soul. And it refers to law, the get them all, the statutes, the precepts, the commands, the decrees, the fear. Okay, so the fear is somewhat of a synonym for understanding the Word of God and obeying it. And that's what Job is talking about. And right, if I may, might ask the question, what justifies my faith in God that I can trust His Word? Well, my response is, look to the heavens. Okay. Thank you for listening. I left some time for questions. Question?
If dark matter can't be measured, but you can see its effects, does that mean it's maybe fourth dimensional or something past our 3 dimensions?
Okay, so we don't know. We do have some ideas. I would classify your idea as perhaps we don't understand how gravity works, which is a lot of people, that's not the usual path people are taking, but that's, I think it's a possibility. I should make myself a little more clear. When you're talking about multi-dimensions, my mind immediately goes to string theory, which is particle physics theory, which tries to tie together quantum mechanics and general relativity, which hasn't been done yet, right? That's why. So that's when you say dimensions, that's what I think. The usual explanations for dark matter are perhaps it's a particle which we haven't discovered yet, and it's actually beyond our standard model of particle physics. You'll hear things like weakly interactive massive particle. You'll hear supersymmetric particles. You'll hear a particle called the axion, which is a favorite around here because we have an experiment running at the University of Washington to try to detect it. So there are attempts at explanation, but so far, none of them has borne out, except for the fact that we see its gravitational effects. Maybe.
Are there other theories besides dark matter, dark energy that might explain the behavior of the universe that's gaining traction in recent times?
There are other theories. Just throw something out there, modify Newtonian dynamics. We don't think we understand how F equals ma. Gaining traction, not really. It is, difficulty with any theory is, not only do you have to explain the expansion of the universe, you also have to explain everything that's in it. So, getting the expansion of the universe, okay. Getting, say, motions of stars within galaxies, we can do that. Getting the entire formation of a galaxy, well, can't quite do that with that particular theory. So, in a word, no, but I think it's important, I'm of the philosophy of leave no stone unturned. The fact that we don't know what it is, well, if you got a good idea, let's at least look at it a little bit. Can
you share about the new telescope and how that's changing what you guys can see?
Which new telescope you talking about?
The one that you just...
I spent a lot of time on, yeah. So, a very roomy telescope. All right, sure. University of Washington is part of this project with the National Science Foundation, Department of Energy. We've just completed the building of a telescope down in Chile, up on a high, dry mountain. You want to be high, you want to be dry when you're making these observations. The cool thing about this telescope is that it scans the entire sky once every 3 nights. Right? So that image I showed, back to it. is just a kind of a few hours of data here. You get this? Right, the camera essentially takes this entire picture in an hour. And so why is that important? Well, that's important because, well, there's a lot of things that change. Those supernovae, you like to catch them. You like to catch a lot of them because that helps us measure distances. Asteroids, those are objects that move. There's millions of them out there. In the history of finding asteroids, we've discovered about 1 million. In the next 10 years, we expect to find 5 million more. And then there's other things that change and things like that. So that's the main focus of that telescope. Yeah.
Does all the space junk in near Earth orbit impact your telescope?
Yes. This is a bit of a contention, right? Yeah. Starlink is bad word for us. We understand, of course, the usefulness, but the glints of such satellites. And this has been cleaned, right? Basically, every time our telescope takes an image, there are satellite tracks that we've got to we have to remove. An interesting thing is the satellite tracks are also out of focus because they're too close. If you see pictures, mitigations are in place. We asked the Starlink and such to paint their satellites black or to change the edges. But you change things one way and then something else happens. So if it's trouble. Yeah. Okay, time for one more question. Yeah.
I just really appreciate you sharing all this. It's so fascinating, and I love having this exposure to stuff I don't have access to normally. I'm curious about in your work with dark matter and its relationship with the fascia of the universe. Has it given you any insights into who God is that maybe wouldn't have been something you might have considered or experienced before as as one of us might have experienced? Because this is I love having a perspective of humility and the greatness and majesty of God. For me, that would kind of tend towards a despairing postmodernism, and I'm wondering if there's anything unique to your perspective that would share an insight into God, beyond the obvious.
So right, I've shared some things, but just sort of comparing the size of the universe with us, right? Why are we significant? Of course, I think of Psalm 8. Right? What is man that you are mindful of him? But I think one thing I haven't shared so far that's probably unique to me, right, is that, I kind of understand this stuff, right? And I think this is not a trivial thing, right? I've got 3 pounds of mush between my ears, right? And it kind of wakes up and can comprehend the distances to the stars, how dark matter works, and the model, all right, there's problems with it, but it kind of fits together, right? We're not doing nothing here. We are making sense of it. And it's not clear, say if it was just the universe and me, that kind of thing can happen. And that gives me pretty clear evidence that whatever made the universe is actually a person, is actually somebody who understands me and has put me together in a way that I can understand what he's created. Right? And that, again, that's not a trivial thing. As I hope I make clear.
Let's thank Dr. Quinn.